I had a chat with Jim, like what we should kind of cover. I'm kind of trying to look at blockchain as a way of promoting people to look into some of the distributed system problems. Because particularly in the era of peer-to-peer, a lot of work happened. So particularly with the file transfer or voice over IP solutions that came, a lot of people worked on this, and then like for the last 10 years or so, things kind of a little bit died down. But now again, I think people are a little bit interested in working some of the problems in this particular domain. So before we get into a little bit more detail, let me set the stage a little bit. So what we used to do with something like a bank is we have an account ID and we have certain amount of money in our account. So this is essentially the ledger, whereas when we talk about blockchain, we may have a more general ledger as well, where we may be able to keep track of other assets as well. Say for an example, we may keep track of Rani's land plot. So maybe a plot has a certain number and a certain address, or you can even look at the latitude and the longitudes. And maybe even, let's say there's someone who grows banana or mango, something like that. But this may not be just mango. You may want to say where it came from, where it originates, or even whether this is organic or not. If it is organic, like what is your certificate number and things like that. So a general ledger would maintain essentially any type of asset, not necessarily money as well. So when you talk about blockchain, we are concerned about everything, not just money, pretty much anything that we can put on the chain. But that is a centralized ledger, whereas when we go for decentralized ledger, what we have is essentially multiple copies of this ledger. Say and this ledger is to be not really maintained by a bank or a certain authority. Maybe authorities may maintain a copy like what we have at the bottom. But generally what we expect is any individual like us, even if you have the capacity to maintain this ledger. But whereas we say blockchain is a distributed ledger, whereas in actual implementation today, blockchain is a replicated ledger. So all these three individuals or people in this case maintain pretty much the same record. So it's quite not true to say it's a distributed ledger. It's primarily a replicated ledger, whereas a distributed ledger would look like this, where you don't necessarily have each and every ID replicated everywhere. So you may want to have a little bit of replication simply because, let's say, there's Bob here and there's Bob here as well, because if this node fails, still we have a record of Bob. But we don't want to record each and everything. So this is a problem already in the current domain. So for an example, the ledger size of something like Bitcoin is about 200 megabytes. Whereas in something like Ethereum, it's about 600 megabytes, but they also say you don't really need to keep the whole ledger, only need to keep part of it. So they claim it's like about 50 GB is what you need to keep. But what will happen is, whether it's 50 GB, whether it's 200 GB or 600 GB, it's going to grow. More and more transactions that we do on blockchains, more and more people, more and more individuals that we bring into the system is going to grow. So going forward, I will primarily talk about the examples using only the money as the assets, but even other things that we can consider in ongoing discussions as well. So one of the biggest problems is when you have multiple copies of this ledger is how do we keep this consistent? Say for an example, Alice wants to transfer 300 rupees to Bob. And in that case, Alice should change her ledger as well as also inform Bob. And let's say in this case, this is Peter, that we are transferring 300 rupees. So in that case, it should get deducted from Alice, whereas it should get credited to Bob. So if we can send this message to both Peter as well as Bob, not a problem. But what may happen is, in real world, we may have certain challenges in doing this. And the other thing is, when we have more and more copies of this ledger, for each and every copy, we need to send a message saying, I'm transferring something from one account to another. So the number of messages will increase when we have more and more copies of the ledger. But then the reality kicks in, where some of our messages may not get delivered. So the message went to Bob, so he updates his ledger, whereas message never reaches Peter, so he's unable to, or he doesn't even know there was a transaction where it says 300 rupees was transferred to Bob. So this creates a problem of consistency. We have 3 copies. Now in this case, I have not updated this one, but we can update this as well. So only these 2 will be consistent, whereas Peter is not. So these are some of the challenges that we have to address in this domain. And this problem is going to get worse when you have more and more copies. So let's say if there are 50 copies of the ledger, getting the same message to all the 50 nodes or all the remaining 49 nodes, it's challenging enough, because some way or another, either a message would get significantly delayed or it may even get dropped as well. But then we are primarily more concerned about this one. So this is typically when people talk about blockchain or even Bitcoin or something like that, they would start talking about double spending problem. We don't necessarily talk about this problem that much. We talk typically the double spending problem, because blockchain is designed to prevent this from happening. But when you have multiple copies, again, you can try to game the system where Alice says, Bob, okay, I'm going to give you 300 rupees, whereas Alice also go and tell Peter, I'm going to give you 400 rupees. Now, if Bob and Peter never talk to each other, they would not realize Alice has spent this money twice, because now she has spent 700, whereas her account has only 500. So this is the double spending problem, where you don't have enough money, you ended up spending by telling different people different things. So in this case, again, the consistency of this ledger is important, because we cannot have a scenario where Alice here has 200, whereas she is having 100 here. More importantly, she has spent 700, which she does not have. So these are the other problem that we are primarily going to deal with. And then again, if you are an attacker, if you are trying to do double spending, more copies that you have in the ledger, that is better, because you can go and tell different copies, here's what I'm doing, here's what I'm doing, I have this much money. So again, the problem is, how do you keep this ledger consistent? So generally, when we start talking about, or when you start learning about blockchain, you would get enough problems trying to understand public key cryptography, hashing, Merkle trees, and things like that. So that is the theoretical side of it. But when it comes to really implementing, there are a lot of other issues that we need to deal with as well. So there are some of the distributed system problems comes in. So if some of you may realize, okay, I can't really get my head around blockchain, it's not only because it's not only cryptography and hashing, because there's also some form of distributed systems involved here, because at least you may have heard of Byzantine failure problem, or how you enforce how consensus. So I'm going to focus 3 common problems that we would see: the timing and the ordering problem, and the consensus problem, and related to this one, again, the cap theorem as well. So if you are working in the distributed system domain, usually you know what is cap theorem, or you have to have some sense of cap theorem, because certain systems that we build may not work at all if you are completely clueless about cap theorem. But interestingly, even today, we don't see a lot of researchers who working in the distributed system domain working on blockchain. But there are other people who are, let's say, not necessarily the hardcore scientists working on this domain, probably because they see the value that this can bring in, as well as the money that this can bring in as well, particularly because of cryptocurrencies. So let's look at again our previous example, where Alice is trying to transfer 300 rupees or dollars, let's say, to Bob. But in this case, now she's not going to lie, she's going to sell the same thing. But I have added a little bit something about timing here. So at a certain time, let's say at 10 a.m. or whatever, Alice initiates this transaction. So she sends the multiple messages to all the copies. And that message reaches Bob at sometime 12. So a little bit later, it reaches Bob. So Bob would update the ledger based on this 300, where he would deduct money from Alice and add to his own account. Now the problem here, and in this case, the same message arrives at Peter much later, at let's say time 18. But in between, so this 12 and the 15, now Bob is having enough money in his account, so he may decide to transfer 1,200 to Peter. So he's supposed to tell this to Alice, as well as he's supposed to tell this to Peter. But the problem is, so Bob sends the message at 15, little bit later it is received by Alice, and there is enough money in Bob's account. So Alice would accept the transaction. But here the problem is, Peter has not seen this transaction yet, because this is coming much later, a little bit later, compared to this new transaction by Bob. So this is called the concurrency problem. where we are initiating multiple transactions, but order of transactions at different nodes are different. So that will lead to an inconsistent ledger. So there are two problems here. One is Peter will reject this request, as well as the two copies are going to be inconsistent. So this is another problem that we need to deal with, simply because the messages may take arbitrary time to go from one node to another, and they may not necessarily arrive at different nodes in the same order. So then again, the problem increases when you have more and more transactions, as well as when you have more and more copies. Because the same message need to go to so many nodes, it may take time because of that. So the more copies you have, more transactions you have, this is going to happen whether we like it or not. So one way of solving this problem is to think about the timing. So if we could rely on Alice's timing, because she initiated this message at 10. And Bob initiated his request at 15. So based on that, if we order this at Peter, Peter would realize this 300 rupees transaction happened before this 1200 rupee transaction. In that case, Peter could still deposit money to Bob's account, and then from that one and withdraw the 1200. But the problem is, when it comes to distributed systems, this is not very easy to do, because we can't trust Alice because of a couple of reasons. One is, our clocks aren't accurate. So let's say if I ask each of you what is the time, you would tell me different times. Some of your times may be closer, at least to the nearest second, but that's very rare. In most cases, it's closest only to the nearest minute. So when you talk about systems where we are concerned about milliseconds or even microseconds, accuracy of seconds or minutes are not sufficient. So the problem is, we have different clocks. Not only that, our clocks runs at different rates. So that is what is called the clock drift. Other problem is, some of our clocks are faster, some of our clocks are slower. So that is called the skew. So even if we somehow get this sync, like you run a time server, or you connect to a GPS device, and trying to correct your clock, after a while again you will go out of sync. So syncing is difficult, and keeping it sync is even more difficult. And the more importantly, Alice could again try to do double spending by changing the time. So maybe she can set the time to yesterday, or maybe she can set the time to last year when she initiated the transaction. So we cannot really trust the time simply because of that. So generally in this domain, we look for some sort of a ordering solution, because it doesn't really matter whether Alice generated this exactly at 10 or 12 or 9 or something else. What matters is, first this transaction happens, then only the second transaction happens. So as far as we can put these transactions into a particular order, things should be okay. So there are a couple of solutions in the distributed systems domain. So one of the most popular or the easiest to understand is called the Lamport timestamp. I'm not going to talk that much about. It's a very simply a counter, a logical counter, just a variable that you would increment whenever you send a message or whenever you receive a message. So if I have a certain value, if the sender has a different value than my one, I would look at which one is higher. If my one is higher, I would update my one by just +1. Whereas if the sender's one is higher, so let's say I had 15, sender has sent me 22, I will update the new clock to 23. Just a logical clock. That will help us to do something called totally ordered multicast. So the whole objective here is everyone in this network trying to do something, need to send a message to all the other nodes in the network. So this is essentially sending the message to each and every replica in the blockchain. Where we can get these two nodes, in this case P1 and P4, to agree on a certain order. So maybe Alice 300 rupees first, and then Bob's 1200. Or the other way around. Not that one see the 300 rupee first, and the other one see the 2200 rupees first. We don't want that to happen. But the problem is, there are some practical issues when it comes to Lamport's solution. And to some extent, this problem is addressed by something called the vector clock. So Amazon uses this, Google uses this. Some of the real world solutions uses vector clocks. But again, the problem is whether it's Lamport timestamp or vector clocks, these solutions do not scale. So let's say if you have 50 copies, that means you have to send 50 messages to those copies. Not only that, you cannot move on until those 50 reply back to you. So you need an acknowledgement to move forward because every node in the network need to agree on a certain order. So this is pretty slow, and the problem gets worse when you have more and more nodes, or in this case, copies of the ledger. So what blockchains typically do would be, they would say no two transactions for the same account in the same block. So typically if you try to initiate two concurrent transactions related to the same account, usually one of them may be accepted, other one is rejected. So this is one way of solving the problem, because you cannot do two things at the same time if you always guarantee that there can't be two concurrent transactions. So Bitcoin, Ethereum, Hyperledger, all of those enforces this, but unfortunately this leads to low throughput. So we are looking at like three transactions per second, 6 transactions per second. Whereas if you are looking at the scale like Visa or MasterCard, those are like 2,000 transactions per second or 3,000 transactions per second. So this is one of the problems that we have in this domain. Or there are other fast blockchains. Some blockchains would say we can do much better. So there are blockchains that could do 100 transactions per second, or there are even theoretical ones like under certain conditions they have shown that we could handle 500,000 transactions per second. But that is usually based on some sort of a centralized solution. You first write to something like a relational or a NoSQL database, and you give a commitment saying this transaction is acceptable, we could move on, but then later gradually go and store something in the blockchain. So this is pretty much proof of existence, where you would say, I have seen this transaction, my database says this transaction is safe to execute, and we just keep a record, because if something goes wrong, we can always go back and look at what happens in this blockchain. So solutions like Stellar or Blockchain DB support this approach. And again, this could be like fully centralized or semi-centralized. There could be only a single copy with maybe a replica. Or some organization like BigChain DB run multiple copies. You could update one of these DBs quickly and get a response, but then they will gradually go and update. But then the problem is, this is not quite blockchain. This is not the blockchain that we really wanted. The true blockchain that we are really talking about, because now there is a centralization, whereas what we want is a blockchain that is completely decentralized, controlled by all of us, not just a single party. So in that context, we are looking for solutions that are more scalable, where we could have high throughput. We could do, let's say, 200 transactions per second, or ideally like 2,000 transactions per second or even more. And we also want to do this with low latency. We don't want to say like, let's wait till the block is closed after 10 minutes, then you get a confirmation, then again after a while you will realize, well, my transaction is no longer included. So then, the other problem that we have in this domain, I will explain using what is called the two-army problem. So in this case, coloring is a little bit of a problem, but let's call them the blue army. Let's call them also the blue army. So altogether there are 4 of them, and there's the white army in the middle. So if only one of these blues try to attack the white will outnumber them. So you don't want that to happen. So you want ideally both of these armies together to attack the white. So you have a choice of either attacking simultaneously both the blues, or you need to retreat. Because if only one of these groups attack, you are guaranteed that you are going to lose, simply because the white would outnumber you. But so the question, the challenge here is, so whoever the general on this side needs a way to communicate. So let's say if they decide to attack tomorrow, a message should go from one side to the other side, and they need to get into an agreement. Let's attack tomorrow at a certain time. But the problem is, you may try to send something like a messenger. So this is good old days where we don't have wireless communication, encrypted communication or whatever. So your only option is to send a messenger from this side to the other side. But that messenger has to go through the area that is controlled by the white army. So the challenge is how you get these two groups of blue to agree on something, either to attack, if so at what time, or not attack. So in this case, we could look at this as a consensus problem. Between two parties, we usually call agreement. More than two parties, we call it consensus. So in real world, you may have realized how difficult for two people to get into an agreement. It's the same thing in distributed systems as well. And consensus is even harder because we are trying to get an agreement with more than two parties. So you have to send messages, all of them need to acknowledge you. So eventually we will get into some sort of agreement, let's say in this case either to attack or not attack. But in this case, we need to do this under a couple of conditions or constraints. Under unreliable communication. Because this messenger may not be able to reach the other end. Because maybe he get captured, he get killed. Or maybe he is worried that he may get captured, so he is hiding somewhere, and now hours and hours passed, whereas you are planning to attack tomorrow morning. So the message can significantly get delayed as well. So this is what we specifically call the partition tolerant problem. I'll discuss a little bit later. And then there could be failed nodes. So let's say one of the generals says, let's attack, but then for some reason he got a heart attack or whatever and then died. So we are talking about computers, we are talking about processors, threads and things like that. They can easily die. When there is an exception, your program died. So this is called the fault tolerance problem. And there could be misbehaving nodes as well. So let's say one of the generals on one of these sites may be trying to purposefully mislead the other side. Maybe for whatever reason, maybe he got bribed. So this is what is called the Byzantine problem, where nodes are not playing fairly or they are trying to mislead each other. So this is, again, we could look at like the double spending problem, where you tell something to one node, where you try to sell something else. So in this case, let's say the two generals start some sort of a communication to agree on a time slot. So let's say the general on this side send a messenger saying, I have a plan, let's attack dawn tomorrow. So the messenger was lucky enough to go to the other side. So the other general acknowledges this message, because if you don't get an acknowledgement, you can't attack. Because you don't know whether the message didn't go to the other end, or whether the message went to the other end but an acknowledgement did not come back. So sending the message to the other end is not enough. You also need this acknowledgement. But then after a while, the first blue general may wonder, the other general may not know that I didn't get the message, I got the message or not. So there's a little bit of doubt in his mind, because he is not sure whether this one really knows whether I got the message. So he tried to send another messenger, the same messenger again, saying, I got your message, we are ready to battle. Then again, if you think of this general, again he may think, okay, this guy doesn't know whether I got the second message. So he may want to again acknowledge, saying, received your acknowledgement, we are ready to go. So if you remember a little bit from your networking class, TCP has three-way handshaking. So this is three-way handshaking because in most cases we are happy with this. Send a message, get an acknowledgement, send another acknowledgement. But in real world, you may always doubt and you may want to do this forever. So the two generals continue to do this because they may never feel safe that other party really knows what I'm going to do. So this is one of the problems. Because the thing is, we can set a limit like 3 and most of the time that 3 is enough. Your message will go to the other side, you get an acknowledgement, you even acknowledge the acknowledgement. But there is a non-zero probability or there is a non-zero chance that the acknowledgement to the acknowledgement may not receive. So you may need an acknowledgement to an acknowledgement to an acknowledgement. So that is the partitioning problem. So the partitioning problem is actually if one of these messengers, either this one or even one of these, is not able to go to the other side, we have the partitioning problem. Then we cannot get into an agreement or more generally a consensus. The second part of the problem is this major got this message, but maybe before he sent this one, he dies. Or there can be the Byzantine case where this general tried to purposefully mislead him. So where he says, fine, I'm agreeing with you, but he doesn't really attack. So we have 3 things here. One is, we have an unreliable communication happening, where we don't know exactly whether it went through or whether it is delayed. The second thing is, we don't know once they initiate this communication whether they are anymore. You make the request, but after that you are no longer there, so it could be a failure. The third case is you are purposefully trying to mislead the other party. Because in this context, if one party does not attack, we are in trouble. So we need both. So, in this context, there is something called the Cap theorem. This is not like a mathematical proof. This is just an idea that it eventually became an accepted theory, where Eric Brewer in 2000 said, it looks like it is impossible for a web service to provide following three guarantees at the same time. Consistency, so that the cap comes from these three. Consistency, availability, and partition tolerant. So I'll very quickly explain this with an example. So again, we have our ledger. There's the Alice copy, there's the Bob's copy as well. So let's say Peter wants to transfer 300 to Bob. So Peter talks only to Bob in this case. So the message went to Bob. And if Bob also tells that to Alice, anyone looking at either the Peter or anyone else looking at how much money Peter is having, we have the correct result. So where both Alice copy as well as Bob copy would agree, there's only now, okay, I have a mistake. So this should actually be Alice. I did a mistake here. So both will agree that there is 200 rupees in Alice's account in this case. But the problem is, if for some reason, if Alice and Bob cannot talk to each other, if you could do a query and ask Alice, hey, how much you're having, it would say 500 because this transaction never went to Alice. So this is the partition tolerance problem, where there is a network partitioning and two copies are unable to talk to each other. So the problem here is partition tolerant is not really an option. So any network, and when you particularly have multiple networks, nodes will lose the connectivity at some time, at least for a few milliseconds, or could be even hours in certain cases. So in that case, we may find it difficult to keep these two copies consistent. So what the theory says is, when this happens, you have a couple of choices. So partition tolerance is required because at some point, these two nodes will figure out we cannot talk to each other. This is usually a transient problem, doesn't last for long, but there could be a certain time that this happens. So in that case, this is required. So your choice is either to go with A, which is availability, or either to go with C. But if you are running a blockchain, to be useful, blockchain should be running all the time. Otherwise, there's no point having a blockchain. So then the theory says, well, if you want A, you cannot have C. But the whole purpose of having a distributed ledger is to keep it consistent. Because everyone in the network should agree how much money Alice is having, how much money Bobby is having, or how many mangoes we may have produced and things like that. So in that context, we are having a conflict. We want both the availability as well as consistency. So in this context, consistency actually means consensus, because if you have the consensus between these two nodes or multiple nodes, we could achieve the consistency. So in this case, we could kind of consider these two terms to be synonyms. So how blockchain deal with this problem today is essentially saying, I cannot give you any guarantee that your transaction would be included in the next block. So this may happen simply because of issues like network issues where your transaction does not reach a certain node. Or in most cases, it could also happen because you may not be willing to give a lot of whatever gas or cash or coins or whatever as a transaction fee. Because usually in blockchain, you prefer to go for the transaction that gives you the highest transaction fee. So that's another reason. So this kind of gives you like a not so solid solution where I would say you can try, but I can't guarantee that your transaction would be included in the next block. But so that is the first thing that all of these solutions that pretty much do today. And then beyond that, there are two primary approaches of dealing with this problem. One is called the leader election approach, where you would designate a node and say, let this guy decide, or this particular node decide what transaction goes into a block. And the rest of us in the networks, let's believe that particular node, at least for the moment. So the question here is, who are you going to select as the leader? Because whoever you select as the leader, and that leader's block, we would consider as the ground truth. So you have to be a little bit careful in this case, selecting a proper leader. So you may do this based on authority. So there are some blockchains that does this based on authority. Certain organization or certain individual will decide what goes into a certain block. Or we can just do this based on trust. Either direct trust or indirect trust. A blockchain like Stellar relies on this. So they have a solution for Byzantine failure, but still eventually that solution relies on some form of trust, where certain nodes in the network are more trustable than others. Or you could just go for a random leader election, or you can go for something like a voting scheme, where nodes vote and elect a certain node saying you're the one that is going to create the next block. Or there can also be other things like proof of stake. The one with the highest amount of money in the network may decide what goes into the block. So here the argument is, if I have invested my money into the network, if I don't play fairly, the network would fail. That also means my money is what I'm going to lose. So this is again essentially looking at a way of keeping people honest simply because they have invested on the system. So Hyperledger follows this approach. Or some of the other Hyperledger ones like Fabric and Sawtooth follow this voting scheme. Or there's another chain called the Steam that says something called proof of brain. So this is essentially the articles that you write, that you read, where you can vote for those articles. So then again, that will give you some amount of cryptocurrency. So then this is very similar to some extent like the stake. The ones with more stake or ones with more reputation will try to play fairly. But the problem, so the good thing about this solution is this is fast. Because when you elect someone, and that guy would very quickly take a decision what goes in and what does not go in. But on the other hand, we don't really trust this guy. To what extent can we really trust this guy? And the whole solution, whole blockchain's consistency relies on this particular individual that we choose. And we may continue to choose different individuals every round. Or the other approach that most of us are familiar is proof of work, where we give a puzzle to everyone, and we would believe the first node to solve that particular puzzle as the leader in this case. So essentially this is in a way an indirect way of solving, figuring out who is going to create this block or who is the leader. So the puzzle should be difficult enough to compute, but on the other hand very easy to check. So like when we create something like a MCQ exam, this is exactly what we do. You have to do all the work, figure out what the answer, but whoever marked the quiz find it very easy to mark because it's one of those answers. So it's difficult to compute, but very easy to check. And on the other hand, we also need to make sure anyone should be able to complete this challenge. Then only it becomes interesting, because if we know only certain nodes in the network can do, they may have an added advantage. So we want the equal opportunity to everyone. Everyone should be able to compete. And more importantly, the problem should be difficult to game. Say for an example, in Ethereum, this particular problem is designed in such a way you cannot invest a lot of hardware to solve the problem. So there is something called ASICs, essentially hardware ICs that use built-in hardware to solve that particular problem. So they have designed it in such a way, an ASIC cannot do. But on the other hand, in Bitcoin, you could do that particular chain. So the problem here is now, because this is very computationally expensive, it takes more time. So it's a slow process as well as expensive. So whereas we want the transaction fees to be pretty small. So even let's say if you go to a merchant and say, if that merchant says, I will accept your credit card, but I want to charge 2% more, 3% more, we don't like that. So we have the same problem here. Then not only that, there can be multiple truths for a while, because there could be more than one node solving this puzzle at a given time. So this get into something like a fuzzy state, where there may be one chain that includes your transaction and there may be another chain that does not include your transaction. So this creates again a little bit of a fuzzy scenario. And what we do is we say longest chain wins. So whichever the chain that can grow faster compared to any other competitor chain will eventually win. But then the problem is, after a while, you may get a confirmation now saying your transaction was included in this block. Half an hour later, you will realize that chain is no longer valid. So your transaction is no longer included in the chain. So in that case, that is why in something like Bitcoin it should be, Bitcoin chain, you need to usually wait like 1 hour, usually like 6 blocks to really be confirmed that your transaction is included. So if you are something like an e-commerce seller where you have already shipped the item because this guy sent me money and half an hour later to realize that transaction is no longer valid, you are in trouble. So what we are really looking for is a solution that could allow us to do transactions fast. We are talking about milliseconds or maximum seconds, not really like 10 minutes or even 1 hour in the Bitcoin case. And it needs to be persistent. Because in real world transaction, we can't say half an hour later, your transaction is no longer valid. If you got a confirmation, that has to hold. That is what we at least expect from typical databases. And ideally, low cost as well. So that is our second set of challenges. How you do this fast, how we provide the persistency, and how we do this at a relatively low cost. So what has really happened is, blockchains have not really solved some of the long-standing problems. So this consensus problem has been there for a while. Similarly, this ordering timing problem has been there for a while. We have some solutions that work under very specific cases, particularly in relatively smaller networks. But not in something like blockchain where you have 100 plus nodes at least keeping the same chain, or millions of users trying to contribute to the same system. So what we essentially have today is a system that works, but under certain assumptions like your transaction may not be included, you may need to retry, no concurrency and things like that. So it's slow, no guarantees, high cost, and not so scalable. But this works, so that is why a lot of hype is there, that is why everyone is interested in this technology, because we hope we could address these problems as we go on. Because it's only started like 2008, only 10 years. This is the time that typically any technology would mature. Usually you need about 10 plus years. So what we are really looking for is a system to, like, if you really want to adopt blockchain at massive scale, we need low latency transactions where inclusion guarantee is there. You're not going to come back later and say, no, you are not included. Fast communication, persistency, high throughput, and not even high throughput concurrent transaction. Because let's say if I'm at the scale of Amazon, thousands of transactions happens per second. So I can't be saying, wait another 3 minutes, wait another 5 minutes so that the next item can be processed. So concurrency is extremely important as well. We want to do this at low cost because proof of work works, but at a very high cost. So we need to deal with that problem as well. And then how we have a truly distributed ledger where everyone does not keep the same copy in each and every node. So what we have is a distributed one, replicated one. We really want a true one. So then how do we go beyond proof of existence? Because the faster solutions give us most of these, but not this. So you also want beyond proof of existence where our transactions are actually recorded in the chain real time. And we have a much better guarantee simply because of that. Where we don't rely on any central database or something like that to do this. So going forward, I believe we need to address some of these challenges. We cannot really go around. We have been going around. And simply because solving these problems have been difficult. So that is why various new solutions have come up. So it's good because whatever blockchain has done today did not exist before blockchain. So some of these ways of relaxing transactions, proof of works and things like that didn't really exist in massive scale. So today we have. So we need to deal with some of these. So at least I hope, particularly the money associated with various forms of blockchains would motivate people to look into this. And definitely we already see, like if you go to any other forums, people are talking about how to improve Ethereum, how to improve Hyperledger, how to improve the Bitcoin blockchain and all of those. So that's my last slide. I'll stop here. So maybe any questions we can take later. Thank you.